Goldberg CP is a version of CP where the homonuclear proton-proton dipole coupling is removed by Lee Goldberg radiation. So it's actually quite nice. So if you're interested at the end, I can come back. I want to switch to talk about studying slow motion by exchange NMR in a solid state. And I want to use this tensor treatment again, even though it is a slightly unusual way of thinking about things. But let me anyway go on. Slow motion is in many ways easy to study. And what I'm describing is the solid state analog of the solution ZZ exchange experiment. And the difference primarily is that for a solid state, you can study slow anisotropic motion and figure out the tensor orientation change and not necessarily isotropic shift change, right? So the idea of 2D exchange NMR is depicted here. You have the simplest version, 3 pulses, 90 degree. After the first 90-degree pulse, you have evolution. And then you store the magnetization along Z by a second 90-degree pulse, and then you wait a mixing time during which your molecule can reorient. And then after a certain time, you flip the magnetization back to the transverse plane and you're ready to observe that signal. The important process that we want to think about is during the T1 chemical shift encoding, your molecule has an orientation, let's call that theta 1 angle. It has omega, a certain frequency associated with that. And then during the mixing time, hundreds of milliseconds, the molecule has reoriented slowly to a different angle and therefore will have a different anisotropic frequency. So then by the time you look at it again, detect it, it'll have a different frequency. All right, so you have this beta reorientation angle between PAS1 and PAS2, initial and final. And you can imagine the kind of spectrum that you should expect to see. And don't worry about site resolved nature. This is, imagine you literally have one type of spin system with its corresponding powder pattern. Then you would have omega-1, omega-2 axis, both having powder patterns. But the point is when you correlate the two, you would have the intensities well away from the diagonal because a point that started at omega-1 will change to some other frequency in omega-2. So your 2D spectrum can be represented by a distribution function S as a function of omega-1 and omega-2. And in general, 2D spectrum is a joint probability of what's the probability of observing something that was initially omega-1 later turning into omega-2. And this is something that was very well developed to the exchange NMR analysis of polymers that used to be the Mines group work. And I find these powder patterns to be quite beautiful in two-dimensional spectrum, always homonuclear correlation. These are simulated patterns for addressing how a 2D exchange pattern will look if you have no exchange, beta equal to 0, reorientation angle is nothing, or you start to grow that reorientation angle 10 degree, 20 degree, etc. And you can imagine when you get to the maximum 90-degree angle, you have really quite amazing cross-peak intensities very far away from the diagonal. And this is assuming a certain powder line shape in each dimension. So this is well exploited. But the issue, of course, is we want to be looking at systems that have many, many different chemical groups and not just polyethylene with only CH2, right? So we want to be able to do things with side resolvedness, and that means magic angle spinning and so on. Before I get to that, I want to just show the corresponding thinking for 1D experiment. So just now, the 3-pulse sequence is for 2D, but if I don't increment the T1 and just choose one and fix that, and then I can go through the same mixing time exchange, and then I will get an echo as long as I wait the same amount of time, T2 equals T1, and let me call that TE, then at this point, you should expect an echo. So this is the stimulated echo experiment involving 3 90-degree pulses, and there's no incrementation of the T1. A 1D 3-pulse stimulated echo experiment is basically an analog of the 2D exchange NMR experiment. And this being 1D, you can then measure things more rapidly, and you're not incrementing the evolution time. This is now a time domain experiment, and you can instead focus your attention on incrementing the mixing time. You can imagine if the TM is short, there's not much of the echo intensity drop. If you wait TM long, then this echo intensity will drop more, right? So you can follow the TM to map out the correlation time tau c for your slow motion. Okay. Back in the normal 2D exchange thinking, your 2D time domain signal can be written as ft1, t2. So then it's complex exponential in the t1 dimension times complex exponential in the t2 dimension, and then you have to do powder averaging. So you get this kind of mathematics representing the 2D time domain signals. When you are dealing with 1D stimulated echo experiment, then T2 and T1 are the same, and they're both, we call it TE, E for echo. And when that's the case, then you will find that the intensity, the magnetization at time TE can be written in this way. It's simpler. And only those segments that don't experience frequency change would actually give you echo intensity back 1. So that's the idea. So this being an echo experiment, any segment that has gone through the reorientation, their signals will be gone. They will not be picked up. And whatever remains as your echo represents the segments that haven't moved. What this means is that 1D stimulated echo corresponds to the diagonal of the 2D experiment. Even when you have a really nice 2D exchange pattern, you always will have some intensity remaining on the diagonal. Diagonal means omega 1 equals omega 2. And that means these are the segments that haven't changed the orientation. So segments with frequency change, you would have to write down their signals as e to the I omega theta 1 TE times e to the I omega theta 2 TE, and so on and so forth. And when you wait long enough, those will approach 0, and only those segments that happen to not have reoriented will survive, and those contribute to your 1D signal. Hope that's clear. So 1D stimulated echo intensity corresponds to the 2D diagonal intensity. Okay, so 1D stimulated echo is a viable and meaningful technique to study slow exchange. Now we want to do this under magic angle spinning. Previously, you might think, okay, I haven't brought in spinning in any sense, but now I want to talk about MAS. Now, under MAS, right off the bat, you have to think about how to get the anisotropy back. If you don't do anything, your CSA will be gone, your dipolar coupling will be gone, and that's not useful because I want to be able to probe orientation. So this is Klaus's experiment where he has these pi pulses coming out like a Redor fashion, except that it's just one channel, not involving two channels. And so every half rotor period, you have a pi pulse, and this will recouple the CSA. Great, that's all I wanted to do. I want to encode the chemical shift anisotropy. And then I want to do it again in the second half. So this is meant to be equivalent to the static doing nothing situation that already has the CSA. Now I just need to put these pi pulses to generate the CSA. A little bit of detail that's important. These two 90-degree pulses that store and then read out the anisotropy, those pulses have very carefully designed phases. The reason is you want to have these phases x minus x, y minus y to be such that you, in two scans, well, when you do phase cycling, you're talking about one scan, I do this, the second scan, I do something else. You want two scans to come together in a certain way. The first scan, you want to have cosine modulation, product of cosine, and cosine argument phi1 for the CSA anisotropy of phase from the first pulse train, and phi2 for the second one here. So you want to have cosine for the first scan. And then the second scan, you switch to the Y phase in order to generate sine. And between the two scans, you want to do subtraction. So you have a cosine minus sine. And that corresponds to cosine phi1 plus phi2. And you can show, keeping track of sine, that this is basically equal to cosine of the phi2 absolute value minus the phi1 absolute value. And these phis are written out here. They're basically the recoupled CSA phase. Okay? Why do I want to generate this? This is meant to be the same thing as the static stimulated echo. The idea being that if there had been no motion during the mixing time, then phi1 and phi2 should really be the same. And I would then get cosine 0, which is 1. Okay? If there is slow motion, however, then omega 1 would change from omega 2, or omega 2 would change from omega 1, then the phase would change. Then this cosine phi 2 minus phi 1 would be a number less than 1. And that means my echo intensity will drop. It's not the full echo, it'll dephase. So this is what we are interested in measuring. You need to do a control experiment to have S0 because you need to control for T1 relaxation. That can be quite significant as you're waiting for hundreds of milliseconds here. So that needs to be taken care of. And the way to do that is to switch the TM and TZ, put a short TZ in the front so that there's no chance for the molecules to move, very short, 1 millisecond. And then the second one being long. So between the two experiments, you have the same combined TM and TZ. So then they get the same T1 relaxation time, you factor that out. The codec signal is S over S0. And it, in the end, is a T1 relaxation free expression of the CSA phase change. And this is cosine phi 2 minus phi 1 and so on. This is where I need to speak about difference tensor, because you see that for this exchange experiment, you're really looking at how the chemical shift anisotropy has changed between one time period and another. And that is the opposite of the average tensor idea. For fast motion, here is the difference tensor. So it's sigma A minus sigma B, and I can call that delta, the big delta. Again, how do we figure out the delta tensor? We want to think in terms of symmetry, and when you do subtraction of two tensors, the reflection of the Z and ZB axis with the bisector plane should give the opposite sign of the original difference tensor. That basically is like saying sigma A minus sigma B is the opposite of sigma B minus sigma A. And by that symmetry, I should still be able to figure out the orientations of the three principal values of the difference tensor. All right, so let's see if we can understand this. Reflection of the ZA-ZB axis with the bisector plane should give me opposite of the original difference tensor. So if I have uniaxial interactions to start with, the easy one is always, let me take a perpendicular one to both initial vectors, or both ZA and ZB. And then I should have one axis in a transverse plane, which is on one side of the bisector, and then the other axis on the other side of the bisector. And these two axes should be perpendicular to each other. Okay, do you see that? So if I reflect the ZA-ZB around the bisector, I should get the opposite sign for the difference tensor. And that dictates how I expect the difference tensors 1, 2, 3 axis should be. 1 and 3 should be the two sides at 45 degrees from the bisector. When you do this, then I can write down the angle from these difference tensors principal axis to the original A and B Z axis. I have these values, and the difference tensors principal values would be 1/2 delta 3 cosine squared theta for one of these, this set, minus 1, minus the second set. All right, so that's how the difference tensor principal value should be. Then if you work through the set, I have, this is general, I say I would just call the reorientation angle between the two, the A and B, to be beta. And then with respect to the ZA axis, the three values, omega A, 1, 2, 3, will come out this way. And with respect to the ZB axis, these are the three expressions. And then you say, okay, I'm going to calculate the difference tensors principal values, you do subtraction, and then you get these terms. So this is the one size fits all principal values of the difference tensor for whatever beta reorientation angle you have. If you're just talking about one uniaxial tensor moving from one orientation to another. So these principal values depend on the beta angle, reorientation angle. These are sine beta functions. And you can see that basically one principal value is in the middle and the two other ones are equidistant in the middle. So this difference tensor has a symmetry parameter of 1, has a hand shape. And then the distance between the two outer principal values will be the omega-3 delta minus omega-1 delta, and you get something that's dependent on sine beta. So the anisotropy scales with sine beta, which is equivalent to beta for small angles. And for typical angular dependencies in NMR, usually you follow the second Legendre polynomial, which is 1/2 3 cosine squared beta minus 1. And if you work through for small beta, take that function, you get beta squared. So a small angle, if you square it, it's an even smaller number. So for typical orientation dependence, you will not sense small amplitude motion very easily. In codex is a little bit better because it only scales with the angle in a linear fashion. So that's an interesting detail. These figures are taken from Klaus's original publications on codex to express how you get that orientation angle information as well as number of sides. I'm not going to talk too much about this because I don't look at the slow motion geometry that closely, but it's understood on a simulation level in principle if you have interesting material systems. But I would talk about this simulation. This is useful. What you're looking at here is intensity, codex intensity as a function of delta NTR. So what is this delta NTR? The delta is the anisotropy. NTR is how many rotor periods of CSA recoupling you want. So this is the part of the pulse sequence where you might imagine as an experimentalist, you not only can control the mixing time, which is the first thing you think about, but you also control how long you want to do CSA recoupling. If you have a very large CSA, then it's going to be super sensitive to any small angular change. Then you don't need to wait very long for that CSA pulse train recoupling to sense that this molecule has rotated a little bit. But if your CSA is quite small and your molecule is moving a small angle, you have to wait longer time in order to encode that chemical shift frequency difference. Right? So you see that there is naturally sort of an inverse relationship. And so the delta NTR, how long you should do the recoupling, should be inversely related to the size of the CSA. And it should also depend on beta angle, this reorientation. This is a parameterized plot. Let's look at the black curves. You have relatively large reorientation for your motion, 70 to almost perpendicular. So if that's the case, then you don't need to go out very far. You can say, all right, I know what my delta is. And based on the simulation, if you can get delta times the time to be about 4 pi, you can see plenty enough of that codex exchange. But if you have very small reorientation, just a little bit of wiggling, then you kind of have to make your NTR relatively long for a given delta. You want to get out to 10 pi or 12 pi. So how long you recouple depends on what you think is the size of the reorientational motion, that beta angle, and it's inversely related to your delta. If you have a very large CSA, you make it easier to detect. Okay, so this is what I want to say about the slow motion by exchange NMR and the MAS, which is the codex. I can summarize the solid NMR-based studies of molecular motion for fast and a slow regime. Fast motion average interaction tensors narrow the line shape, even though most times we don't directly measure the line shapes very much, but in a time domain, we can get that piece of information to some extent. The average tensor and spectral line shapes of several problem motions can be derived analytically based on the symmetry of motion. So that's very nice. Fast motions can be experimentally measured using experiments, dipshift class, a family of experiments. And all the parameters, really didn't talk too much here, provide information on rigid body motions as well as internal motions. Switching to the slow side, you can use the equivalent of 2D exchange static NMR, which is 1D codex to get information about millisecond time slow motion. And slow motion geometry is described by difference tensors. So then I have a short talk about how to study biomolecular hydration, water accessibility by solid state NMR. And this is quite useful. Most of the time in my group, we deal with hydrated samples and semi-solids. I think that's probably true for a lot of chemical systems as well. And so hydration is very important for biomolecular systems, whether you're talking about channels with water-filled pores or cell walls and ice-binding proteins, globular proteins, microcrystalline proteins with water molecules, amyloid fibrils. People have tried to observe water in these amyloid fibers. So water is important, and water-edited NMR experiments are really pretty straightforward to do because you basically add a simple T2 filter module on top of existing multidimensional correlation experiments. Here are some of the pulse sequences we have used in my group, and they are all basically experiments where you start with a water-selective T2 filter, a soft pulse, a 180-degree pulse in the middle of a T2 filter, or you can start with a soft 90-degree pulse, Gaussian pulse, and then you go on with a T2. Why do you need a T2 filter? You would like to destroy the rigid systems magnetization, rigid protein that we don't want, and then you keep only the water magnetization, then you can transfer. The transfer is described by this longitudinal mixing period, we call it spin diffusion period. And then subsequently, you can do 2D carbon-carbon correlation or 2D nitrogen-carbon correlation or 2D nitrogen proton HSQC kind of experiment. So that's this version. These experiments are nice because they tell you which sites in your protein are particularly water accessible, which sites are dry. And that's a very nice, useful piece of information. So I want to give you a few examples. We have studied the tau protein a lot recently. Native tau is intrinsically disordered, but under various conditions, it can form amyloid fibrils, and that's detrimental in human brains. And we're trying to understand the amyloid forming mechanism, what kind of structures you have. We get structural models like this. This is a low resolution model, the full length tau, one of the isoforms. Then we like to ask, well, in this U-turn shaped beta arch structure, are there water molecules? What's the degree of hydration? So this is when we run this kind of water-edited 2D carbon-carbon correlation experiment. When you look at the normal 2D CC spectrum, you can have all the sites, you assign them, you've done the hard work, and then I go in and start the water selection, and then I give it a short mixing time. So I don't allow water to equilibrate and hydrate everything. I retain some heterogeneity, and the intensities are, of course, lower, but usually you can manage that. And when that's done, you can then look at the intensity ratio between the water-edited short mixing time spectrum versus the equilibrium spectrum. And then when you do that ratio, you basically get a we call hydration map, where different residues have different degrees of hydration. So here, bluish, greenish intensities are particularly high. So these are well-hydrated serines, and then the reddish residues are less hydrated. So that's the kind of experiment you can do. Here is an example where we have 2D nitrogen carbon correlation as the readout. And again, I have the assignments in the equilibrium spectrum. And once I add water editing, then I get a hydration map, and you have some sites that are very dry, other sites much more water accessible. So you can quantify intensities in this way to figure out which part of the protein is water accessible. And in the case of tau, this particular sample of 0M4R tau, we found that in this beta arch, there's a zone in the middle here that has more water accessibility for the various residues that flank both this top part and the bottom part. And that came from the site-specific analysis. Okay, so now we can run MD simulations. We can give ROMAX the low resolution model of the backbone, and then let it find out how much water can actually permeate into this fold. And so these red balls are showing the water oxygens, and you get a sense that there is some water inside this beta arch. We can apply the same concept to membrane systems, membrane proteins, alpha helical bundles that make ion channels. And we have studied the SARS-CoV-2 envelope protein for a few years now. And you can see that when we do this water transfer to 2D nitrogen carbon correlation experiment, we have a lot of sites that are pretty dry, but then a few spots are relatively wet. And so that gives you a sense of which residues are water phase. More recently, we have studied, okay, this is a typo, should be SARS. We are looking at, this is unpublished work. We created a state of the SARS E protein that is open. And what we mean by open is that basically you have water in a channel, and you can tell that just by measuring water NMR. And we create that state by going to low pH and then add calcium, compared to the closed state, which is high pH and no calcium. Okay, so if you look at the spectrum, a very colorful spectrum, and that's because I'm not showing you the original spectrum, which there are two, an equilibrium 2D-CC spectrum, and then a water-edited spectrum with a short mixing time, and then I divide, and my contour lines are showing you that intensity. And so under the same mixing time conditions, for the neutral pH sample without calcium, most of these intensities are low, shown in red. And when you go to the low pH acidic sample with calcium, most of these intensities, divided values are relatively high, more greenish. So that means that in the side resolved hydration map, that this entire protein, when you have subjected to acidic pH and calcium, it has become more hydrated. So this allows us to say, without doing electrophysiological measurements, which we don't do, we can say biophysically, these conditions generate a SARS-E protein, which is more water accessible. And that is basically for ions to be conducted an open state. A more modern version of the water edited 2D experiment is this nitrogen proton correlation as the readout preceded by this water editing. Okay, and here, why do I keep writing this proton T1 saturation recovery? It's because, let's see, you do this when your tau SD, this mixing time is getting to be long. And the reason it's long is because if I'm doing proton detected experiment, I'm spinning at 50, 60 kilohertz. So it's pretty fast. And when you're spinning that fast, your water polarization transfer to the protein becomes kind of inefficient. So instead of only a few milliseconds for that transfer to occur, you find yourself having to use tens of milliseconds or even 100 milliseconds. And when you do that, your intensity will drop just by T1 relaxation. So you need to take care of that by getting the accurate intensity by having a T1 measurement, T1 saturation recovery measurement. All right, that's a technical detail. We implemented this for the EMRE sample, which we have deuterated version. So we actually can do experiments at relatively fast spinning of the 1.3 millimeter rotor. So these are the nitrogen proton H&H correlation experiments. And what I'm showing you in gray, so these are overlaid spectrum plots. In gray is the long mixing time, about 320 milliseconds or so. In cyan is the 30 millisecond short version. And the main point we want to convey is that the intensities are not the same. So when you wait only 30 milliseconds, your water magnetization has not equilibrated all your protein residues. Some residues are getting it faster than others. And so that's the information you are interested in. I don't show any further analysis. Basically want to say that this hydration or water accessibility is different between the blue sample at high pH and the orange sample at low pH. And we have structures for these two states. And we can also put these structural models into GLOMAX for molecular dynamic simulations. And it comes out in agreement with the experimental data, which is basically saying at the high pH, there's a bit more water transferred intensities, and there's more water molecules in the high pH channel. This class of experiments all basically answer the question of how water accessible or how water exposed are your protein residues. So that's one type of question. And the last few slides will give you a slightly different take of water edited NMR. And here we're not only focusing on the amount of water next to protein residues, but also the dynamics or the nature of water molecules next to some residues. And we're doing this for the influenza B virus proton channel, which we solved the structure for. And then we collaborated with a group that does MD simulations that can tell us about, okay, what do these channels look like in the closed and open state in terms of the interior, the water permeated pore. So we did all these MD simulations. We can analyze various things, the water molecules, what are the translational motion, what are the rotational motion of water molecules. But experimentally, what we can do is first we say, okay, let's do a water edited experiment here. I'm having a soft pulse 90 excitation, and then I do the T2 filter, transfer to carbon, and then I can compare the closed state and open state of BM2, high pH, low pH. And then I can say, okay, I see some difference in the water transferred intensities, and the red sample, the low pH sample, gets the water magnetization faster compared to the high pH sample. So that means, okay, the low pH channel has more water molecules. So that's one piece of information. And that's the same accessibility information you are seeing in these other examples. But an orthogonal type of experiment is that in addition to transferring water magnetization to protein, before you let it transfer to the protein, you can insert something interesting here. You can do a spin lock experiment while the magnetization is still on water. And the spin lock is done in a way to recouple anisotropic interactions. This is a sequence that exists in the literature. We basically match the spin lock omega-1 to 2 times the spinning speed. And it can be shown separately that that's the condition for recoupling the CSA. And now you realize this is the CSA of water, not the protein, because I haven't transferred the water magnetization to the protein yet. That transfer happens in this block after my spin lock, right? So at this point, I'm still probing the water anisotropy. And you might say, well, what do you mean water anisotropy? Water molecules tumbling randomly. You might imagine that it might tumble randomly in a channel, but I can tell you no. Experimentally, we actually are observing oscillation. And what is this oscillation? I'm looking at the intensity of water as a function of the spin lock duration, tau SL. I'm growing this duration. I'm following that. And if there's no anisotropy, if my water molecules in this channel are isotropic, then this recoupling won't recouple anything. There's nothing to recouple, right? If you have an isotropic fast tumbling system, CSA is 0. Then omega-1 equals to omega-r won't do anything for you. And if that's the case, you would simply see single exponential decay because there's T1 relaxation. But instead, I see a little bit of oscillation. It's not an exponential decay. And one can fit this oscillation to a finite residual anisotropy. That residual anisotropy is slightly different between the acidic red sample data and the neutral pH black data. You see that the red data oscillate a little faster. The minimum comes out at a shorter time. Faster oscillation always means a larger interaction, right? So a larger residual CSA. And so this is really cool. Acidic pH, I know that BM2 channel is open. It's a wider pore. And you might say, well, if it's a wider pore, the water can tumble isotropically. Why should it be more anisotropic? That sounds wrong. But it's not wrong because this channel conducts protons. And water is serving as the Grotthus hopping conduit for the protons. The protons are going from one H3O plus going to the next H2O. This, you have these water molecules partially aligned in the channel so that it can facilitate the hydrogen bonds that need to be there in order for the excess proton to hop down the water wire. And so if the water molecules are all random, then you cannot have the Grotthus hopping. So there needs to be a little bit of residual alignment in order for this Grotthus hopping to work, to deliver the excess proton to the histidine residue. And then the histidine can do the ring flip and release that proton, and then it goes down the remaining water wire into the nucleus. So our computational collaborators then look at the trajectory, the file of water molecules in the channel, and can actually quantify what's the most probable water orientations along the channel axis. And they're showing here. On the left is the closed state of the channel. You have the oxygen in red, and then the open state on the right, H2O orientation is shown. On the right, there's a little bit more residual alignment. And above and below that crucial histidine, you can see that the water orientations kind of flip above and below. So the water molecules above the histidine point the oxygen down, and the water molecules below the histidine point the oxygen up. And this is interesting for this whole proton relay process. You're having that excess proton being relayed by a mixed hydrogen bonded chain of partially aligned water molecules with the histidine ring. So in that particular study, we find experimentally from this measurement, what's the residual delta CSA? I should have a bar there to indicate that it's mostly average CSA, 1.8 ppm. And you can then go into the literature and figure out what exactly is the CSA size for immobilized water, i.e. ice. You can dig out that information. And you find that taking the ice, water proton CSA of about 20 something ppm, you get an order parameter here, which is about 6% for the low pH situation. And you go to the high pH sample, the residual CSA is 1.2 ppm, and the order parameter is about 4%. So it's a little less ordered. Okay, so this is another interesting take of the water additive where you do something more special with spin lock. So it's not just the amount of water, but it's also the dynamics. You can imagine that this can be extended to a lot of systems. Okay, forgot to mention that you might say, why do so many transfers? Why not just do it on the proton side and then detect? Why go through the trouble of transferring to the protein? The only reason we do that is because in typical biomembrane samples, there are lots of different types of water. There's the water inside the pore, but that's a tiny fraction of the total water. There's the bulk water, and then there's the water on the membrane surface and so on. And if I observe all the water, I will never be able to tell what the maybe 5% of the channel water is doing. And so I need to be able to detect on the protein side to grab the situation of the water molecules next to a protein. So that's the reason. So water transfer NMR experiments as detected on the protein side is very, very useful. And it gives you a lot of biophysical insight about your system. So I encourage you to try it. It's not hard to do. And if you have simpler chemical systems, you don't need 2D detection, then 1D works.